So the problem of the day from last time, since the exponent is negative, that means that we have to move the decimal point to the left 6 times. So that means we will have to put in 5 zeros. The next part of this problem said that we needed to write the number in words. So we write the number as if it were a whole number first, so 5,000. $300. $25. And then we need to name the position of the last digit. So we have tenths, hundredths, thousands, 10,000s, 100,000s, millionths, 10 millionths, 100 millionths, billionths. So the 5 is in the billionths position. And there it is.
I was doing it like at the top. Like how there's like 3 over here, I was like 1, 10s, 100s, and then that's 5.
But you needed the new number in words. Okay. Section 4 homework, page 426. Any questions?
Oh yeah, why aren't we doing 4.5?
We are skipping 4.5 because cycle 4 was really, really, really long. So we just went through it and figured out what can we skip, what is it that they really do not need to know at this point. And this was one of the sections. If you take statistics, you'll get it in statistics. Section 6, let's go to page 435. It says complete the following table using these steps. Number 1, complete column 3 by writing the column 2 numbers in scientific notation. Okay, so the first number. Where do we need the decimal point to be to write this in scientific notation? Between the 5 and the 7. So 5.791 times 10 to some power. What should the exponent be? 10. What about Venus? Between the 1 and the 0, so 1.082 times 10 to the 11th power. Let's skip down to Saturn. What about Saturn in scientific notation? Between the 1 and the 4, so 1.4294 times 10 to the 12th power. And how about the last one, Neptune? Between the 4 and the 5, so 4.5043 times 10 to the what power? 12th power. Okay, so you can fill in the other 4 later. Let's see, number 2 says complete column 4 by converting the column 3 numbers to kilometers. Keep the numbers in scientific notation and notice how the exponents in column 4 compare to the exponents in column 3. Okay, so we're converting meters to kilometers. So meters to kilometers, we would move the decimal point 3 places to the left. So far, so good? So if we go down to our number for Mercury, and move the decimal 3 places to the left, we would need 2 zeros, 5791 times 10 to the 10th. So we just moved the decimal point 3 times so far. Okay with that part? Okay. Now at this point it is kilometers, but it's not in scientific notation. Where do we need the decimal point for it to be in scientific notation? Between the 5 and the 7. 5.791. That's going to change the exponent as well. This decimal number is becoming larger. What's going to happen to the exponent? Smaller. They go in opposite directions. So, and we also moved 3 times, so the decimal is going to get smaller by 3, so it will become 7. So for mercury, under kilometers, we have 5.791 times 10 to the 7th power. Let's do Venus. So we have, okay. Again, like before, if you're looking at the chart at the top, still have to move 3 places to the left. So we're going to have to put 2 zeros in front of the decimal number for Venus. So 0.001082 times 10 to the 11th kilometers. But now we'll have to convert that to scientific notation. So 1.082 times 10 to the 8th power. Very good. Again, it's a matter of reducing the exponent by 3. So if we skip down to Saturn, can you go directly to the answer? What do you think it would be? To the 9th power, yep, 1.4294 times 10 to the 9th power. The last one, Neptune, would also be to the 9th power.
Can I ask a question?
Mm-hmm.
How did you get to the 10th power in the first place? Like,
Okay.
to the 12th power?
So looking at Mercury, we have this really big number. We need the decimal point to be between the 5 and the 7, correct?
Yeah.
So how far do you have to move the decimal point? The decimal point starts out at the end. So if you go to the first comma, that will be 3, 6, 9, and then one more, it'll be 10.
Gotcha. Okay.
Other questions so far? Number 3 says complete column 5 by converting the column 3 numbers to centimeters. Keep the numbers in scientific notation and notice how the exponents in column 5 compare to the exponents in column 3. So now we're converting from meters to centimeters. So we're using column 3 to get column 5. Meters to centimeters, 2 places to the right. So looking at Mercury, if we move the decimal point 2 places to the right, we would have 579.1 times 10 to the 10th centimeters. But we need that number in scientific notation, so 5.791 times 10 to some power. Notice that the decimal number is getting smaller. What's going to happen to the exponent? It's going to get larger. What will it become? 12, because we had to move the decimal point 2. We changed the exponent by 2. So 5.791 times 10 to the 12th power. So how about Venus? What would that be? Sorry? Very good. 1.082 times 10 to the 13th power. If we skip down to Saturn, decimal part stays the same, 1.4294 times 10 to the, 14th power. And the last one would also be to the 14th power, 4.5043 times 10 to the 14th. Any questions on that table? Okay, so you can go back and fill in the missing ones later. Let's go to page 436. Throughout this cycle, numbers in scientific notation have appeared, often with negative exponents. What do the negative exponents really or actually mean? Do negative exponents follow the same rules as positive exponents? Let's look more closely at negative exponents and their properties. So example 1, simplify x squared over x to the fourth in two ways. First, by writing out the factors and reducing, and second, by using an exponent rule. Okay, so first of all, writing the factors. What does x squared really mean? X times x. And x to the fourth power? We have the x 4 times. Well, we have some common factors there. We can cross out a couple pairs of x's. What's left? What's that? I think maybe you were right. I just didn't hear you.
I said x to the second power,
X to the second power, that's part of it. What's in the numerator?
but 1.
1. So it will be 1 over x squared. Now let's use an exponent rule. X squared over x to the fourth. We have the same base of 4, and we're dividing. What should we do with the exponents? Subtract them. We would end up with x to the negative 2 power. Since these are both correct ways of simplifying the expression, the final expressions must be equivalent. Write an equation stating that. So x to the negative 2 power is the same as 1 over x squared. Any questions on example 1? This will be true with any exponent, not just negative 2. So if we had a negative 5, we would move it to the denominator with an exponent of 5. Okay. Example 2. Let's look at patterns with exponents. Continue the pattern by writing the next 3 equations. So x to the fourth is 81, x cubed is 27, 3 squared is 9, 3 to the first power is 3. What do you think the next line would say? 3 to the 0 power is equal to 1. How about the next row? 3 to the negative 1 power is equal to not negative 3.
0.3.
When the 3 repeats, what fraction is it? 1/3. Okay, so I think you see the pattern on the left side. Let's look at the right side a little bit closer. What are they doing as they go from one row to the next row? How do they go from 27 to 9 and 9 to 3 and so on? Divide by 3. Okay. What do you think the next row is? Which is equal to? It would be 1 over 9. Now using that, what we did in example 1, we could actually write that as 1 over 3 squared to make the exponent positive, which is also 1/9. So we can generalize the last statement. A negative exponent means that a reciprocal should be taken. So x to the negative a means the reciprocal of x to the a power. That is, x to the negative a is equal to 1 over x to the a. And for example, 5 to the negative 1 power is equal to 1 over 5. Any questions on that box? Negative exponents play by the same rules as positive exponents. However, it is often more appealing to see an expression with exponents that are positive. Let's look at ways to simplify an expression with a negative exponent. Example 3. Rewrite 5 to the negative 2 power with a positive exponent. How would you do that? 1 over 5 squared. And if we wanted to, we could simplify it. We would end up with 1 over 25.
So it's always going to be 1 over, and then
Well, as long as the exponent starts out in the numerator, then you move it to the denominator. Let's look at what happens at the next part of this. Now let's rewrite 1 over 5 to the negative 2 power with a positive exponent. Use the fact that the fraction bar means division. And we're actually not going to do that. We're just going to see if we can figure it out because I think using the division just is confusing. Any guesses as to what we should do with 1 over 5 to the negative 2 power?
Make it negative. I'm just kidding.
No? At least you guessed. Any other guesses? Before it said when we have a negative exponent, we should think reciprocal.
So put 5 squared on top.
Put 5 squared on top. Very good. So 5 squared over 1, or just 5 squared, and we can simplify that. That would be 25. So if the negative exponent starts out in the numerator, like the first part of this problem, then move it to the denominator. If the negative exponent starts out in the denominator, then move it to the numerator. The exponent becomes positive. So what can we deduce from the example? Basically what I just said. Negative exponent in numerator. Move to denominator. And vice versa. Example 4. Rewrite x to the negative 2 power, y to the 3rd power with only positive exponents. Any suggestions?
Move negative 2 or x to the negative 2 power to the denominator.
Okay. We have to get rid of that negative 2 exponent, so we're going to move it to the denominator. Notice y to the 3rd power already has a positive exponent, so we're going to leave it in the top. So we end up with y cubed over x squared. It's just the x to the negative 2 that we have to move. Questions on example 4? What about example 5?
Flip them.
Flip them. Both of them start out negative, so we need to end up with the y's on top and the x's on the bottom. Any questions on example 5? So at the bottom of page 437, how it works. To simplify expressions with positive or negative exponents, assume a and b are integers and x and y are real numbers. So number one, if we're multiplying, we would add the exponents. That's an old rule that we talked about earlier. When you're dividing, subtract the exponents. X to the 0 power is a special rule. That's always 1. When you're raising to a power, you would multiply the exponents. When you're raising a product to a power, now you have to distribute that exponent on the outside. If you're raising a quotient to a power, again, it's like number 5, you have to distribute that exponent on the outside. Now 7 and 8 are new because that's where we're dealing with the negative exponents. But if the negative starts out in the top, we move it to the bottom. If it starts out in the bottom, we move it to the top. Page 438. For example, we can simplify the following expression in 2 ways. Let's look at method 1. So they started in the denominator and they multiplied those exponents to get x to the 6th. Then they decided to subtract the exponents, and that's how they got an exponent of negative 21. And then they moved that to the denominator, 1 over x to the 21 power. Any questions on method 1? Let's look at method 2. Same problem, but they're going to solve it a little bit differently. They do start the same way. They multiply the exponents in the denominator. That's how they get x to the 6th. And then they decided they didn't want to deal with the negative exponent. So they moved x to the negative 15 to the denominator, made it x to the 15th. And then they could add the exponents. And they still get 1 over x to the 21st power. Both methods are correct, although one is shorter. Choose the method that makes sense to you. Any questions on either of those? Okay, practice 1. Simplify each expression. List answers with positive exponents only. Do not use a calculator. So work on practice 1. Get as many as you can. You may need to skip around. Okay, letter A. What do you think, Alexis?
9.
That should be 9. That one was pretty easy. How about B? Nicole?
1 over, oh, just kidding. 1 over 9.
Okay. It's
That's
actually
right.
1 over 3 squared first, which is 1 over 9. Any questions on B? How about C, Cody?
I guess on this one, I got 9.
9
Mhm.
on C?
Yeah,
Well, notice there's no negative exponents on that one,
so don't flip it.
so don't flip it. Yep. So what should you end up with?
Did I just do 1 over 9?
1 over 9. There you go. You just need to square the 3 to get the 9. How about D, Alexis?
Yep. Over negative 9. Don't know.
Ah, okay. Now you cannot raise to a power until the negative exponent is gone. So we have to get rid of the negative exponent first.
Should it be negative 9 over 1 then? Okay, never mind.
Well, let's flip it first and then we'll see what happens. If we move that to the numerator, what do we have in the numerator?
3 and then to the negative 2nd power.
Not when we move it up. Why do we move it up?
Because it's negative.
Yes. We move it to get rid of the negative
Oh,
exponent.
so it would be like 3 to the 2nd power.
Exactly. 3 to the 2nd power over 1, which is really just 3 to the 2nd power, which is 9. So the negative exponent won't make your answer negative. So be careful about that. How about E, Nicole?
I got 1 over 3x to the 2nd power.
1 over 3x to the 2nd power. You're close. What's the exponent on a 3, even though it isn't written in there?
Or 1.
Right, so it's already positive, which means a 3 should stay on the top. It's just the x squared that needs to move to the bottom. The 3 already had a positive exponent of 1. Questions on E?
How do you know when you can break them up like
It's multiplication, so it's okay to do that. You can flip one and not the other. If it was addition, then you couldn't do that. How about F, Cody?
Is it 9x?
9x, you're close, very close. You're right that you have to square the 3. That will give you 9.
Yeah. 9x. You did square the x too? 9x
Yes, you
squared.
have to square the x as well. So 9x squared. This is when we have to distribute the exponent on the outside. How about letter G? Alexis?
I didn't do this one because I didn't know. Would it be 9x?
We can't raise to a power yet because of the negative. Now there's a couple ways you could start it. If you look back at letter F, it's very similar except for the negative, right? So you could distribute the -2, although you can't actually multiply it out because of the negative. But you could distribute the -2. That will be one way to start. That would give you 3 to the -2, x to the -2. So far, so good? And then what do you do with that?
Well, wouldn't it, like, the two negative, like the -2 or whatever, like, cross out? Okay.
But how do we do that? How do we get rid of the negatives?
Put it in a fraction.
Right. So what's in the numerator?
Wouldn't it be the 3?
Not the 3. Notice both of those are negative, so both of them are going to have to move to the denominator. So what's in the numerator?
1.
Exactly. So when you move them to the denominator, the exponents become positive. So final answer would be
It'd be 1 over. Shoot. 9x squared.
There you go. Now another way to do this one, some people might look at this and say, I'm going to get rid of that negative right away. So you could have started by writing it as 1 over 3x squared. So you could have moved it to the denominator first and then distributed the 2, and you would get the same thing. Squaring the 3 gives you 9, and then the x squared. How about letter H? Again, there's more than one way you could start it. What do you think, Nicole?
I added the exponents, which would get you 3 to the 3rd power, or 3 cubed, and then I got 27.
3 cubed is 27. Good. That's one way to do it. Now another way, again, some people might say, I'm going to get rid of that negative exponent. So then the 3 to the 5th would stay in the numerator, but then you'd have 3 squared in the denominator, and then you can subtract the exponents, which will give you 3 cubed, which is 27. So either way is fine. Cody, what would you do with I?
Multiply the exponents.
And you would get
-3 and -4.
3 to the -4th power. And then what?
Flip it, so it's 1 over 3 to the 4th power.
Which is
1 over 243.
not 243.
Did I mess that up?
It's on the other page.
Oh.
3 to the 4th is
Let's see, hang on. I don't see what you're talking about.
I said I already said it.
Oh, right here, 81.
81. Do you know how to find exponents or raise to a power on your calculator?
Yeah.
Yeah.
Okay.
Use the caret.
This is,
Okay.
Just do not use the calculator.
Okay. Letter J. Alexis, what would you do there?
Okay, so you like subtract the 6 and the 5,
And you would get?
1, then it'd be 3 to the first power, which would make it 3.
Exactly, yep. How about K, Nicole?
You subtract the exponents and you get 3 to the negative 1 power, and then put 1 over 3.
Very good, 1 over 3. Any questions on any of those? Okay, now let's see if we can do practice 2. We'll do that one together. Whoops. I apparently don't have it on there. Okay. Practice 2. Okay, any suggestions for how to start this one? Distribute what?
The exponent.
Okay, good. So we can take this negative 4 and we can distribute to the exponents inside. We would have 3, and then we would have x to what power?
To the 6th?
Not 6.
Oh, no, I'm sorry. To the negative 8.
Negative 8. Y to the 12th power.
Why would you keep that in parentheses though?
You can keep that in parentheses if you want to, but you don't have to. It's all multiplication anyway, so it doesn't really matter if the parentheses are in there at that point.
So you don't have to distribute the 3?
No, you would not distribute to the 3 because the 3 is outside the parentheses. It's just what's inside the parentheses that's being raised to the 4th power.
No,
Negative 4.
I know, but why wouldn't you distribute the 3 to x to the negative 8 and y to the 12?
Oh, because the 3 is a coefficient, not an exponent. You can multiply the exponents, but not the coefficient with an exponent. So the number out in front just stays. We're not going to distribute that to the exponents.
No, I mean
To the x and the y? Because there's no plus or minus in between. If there was a plus or minus in between, yes, then you could distribute the 3 next. Okay, so where do we go from here?
move the x to the negative 8 and
Okay, we can move x to the negative 8 to the bottom. So we'd have x to the 8th. We'd also have an x and a y in the denominator. Now what happens?
subtract the y's.
Okay, we need to combine the x's and the y's. So the 3 is going to stay in the numerator, correct? Now what?
Y to the power in the bottom.
Y to the 11th power in the bottom, do you agree? Why would you move it to the bottom?
No, I say on top.
Okay, if you subtract, you'd have y to the 12th minus 1 would be y to the 11th. Since it's positive, we can leave that in the numerator. What's in the denominator?
8x squared.
No?
Well, you can't do 8x.
So when you're multiplying, what do you do with the exponents? Add them.
X to the 9.
X to the 9th power, there you go. let's go back for a minute to this point here. You know how we took the 12 and we subtracted the 1? We also could have subtracted the exponents on the x. In that case, we would have had the 3. And then if we have negative 8 subtract 1, that would be negative 9. And 12 minus 1 is 11. And then move this to the denominator and we would get the same thing. Okay, so you can do it either way, whatever works best for you. Number 4. Suppose a middle school class is building a model of the solar system. They plan to use a styrofoam ball with a 10 centimeter diameter for the sun. Part A. What is the scale of their model? Write a ratio of the model sun's diameter to the actual sun's diameter. Diameter of the sun is equal to 1.4 million kilometers. You do not need to simplify the ratio. Okay, so we want the ratio of the model sun's diameter. The model sun's diameter is 10 centimeters over, well, 1.4 million is probably best if we change that to scientific notation. So 1.4 million. Let's write it in standard notation first, and then we'll change to scientific notation. How would you write that in standard notation with the zeros?
And then 400, and then 2 more sets of 3 zeros. Does that make sense?
Do we need 2 sets? I think maybe just 1.
Okay.
1,400,000. Now in scientific notation,
1.4.
1.4 times 10 to the 6th power. So if you realize that million means 6 zeros, you could have gone directly to that. Okay, so 1.4 times 10 to the 6th, and that's kilometers. And they said we do not need to simplify it. Any questions on part A? Part B. I'm sorry? Yep, they have the same thing on part B over there, yep. If the entire solar system model is to have the same scale, all the distances must follow this ratio. Find the distance from the sun to each of the planets in the solar system model in centimeters by solving the following proportion. Round each distance to the nearest centimeter. So we're going to start with the ratio that we found in part A is equal to, and then we have the model distance in centimeters, the actual distance in kilometers. So if you look at the table, they're giving us the actual distance in kilometers. So we're going to substitute that into the denominator, and we're going to find that numerator.
Why don't they give us room to do this?
Well, I totally agree on that, and I have less room than you. I'm going to have to open up another page. Okay.
When's all the homework due, do you know?
The homework is due tomorrow. Okay, so for Mercury, we're going to start with the ratio that we had on part A, 10 centimeters over 1.4 times 10 to the 6th kilometers. And that's equal to something over, the actual distance to Mercury is 5.791 times 10 to the 7th power. So we're going to have to use cross products. So if we multiply these two, That would give us 1.4 times 10 to the 6th x.
Can you multiply and leave another centimeters and kilometers?
I'm sorry, what's that?
Like 10 centimeters and then the other one's kilometers. Can you multiply those?
We can multiply those. In fact, we will. What's really happening is we're multiplying by another 10. So it's really just a matter of changing that exponent of 7 to an 8. That make sense? Okay. So we multiply the other way, we get 5.791 times 10 to the 8th power. Now how do we solve this equation? We want to get the x by itself, right? So what do? We divide by the 1.4 times 10 to the 6th power. So all that's left on the left side is x. For the scientific notation, we need to divide the decimal. So take 5.791 and divide by 1.4. And I think you get 4.14, is that correct? If you round to two places. So 4.14 times 10 to the, what do you think? We have the same base of 10.
10 squared?
And 10 squared, right. We're dividing, so you need to subtract the exponents, and you get 10 squared. Well, that number is pretty easy to convert to standard notation. What would it be?
100.
Sorry?
Maybe 100.
Oh, well, yeah, 10 squared is 100, and then times 414 would be?
Or 400.
There's an even easier way. Since the exponent is positive, you need to make the number bigger. So move the decimal over 2, and what do you have?
414.
There you go. So that's the number that goes in the first box. Okay. Now let's do the next part over, the distance from the sun in model. We want to convert, basically we're converting the centimeters to feet. So we have 414 centimeters. We want to convert to feet. Now when we've been dealing with the metrics and in the US system, the conversion between the two, we've been using centimeters and inches, right? Okay. So our next ratio would be
1 inches over 2.54.
There you go. 1 inch over 2.54 centimeters. We can cross off the centimeters. We need another ratio.
12 inches equals 1 foot.
12 inches equals 1 foot. So we need the 12 inches in the denominator, 1 foot in the numerator, so we can cross off the inches. So we have 414 over, what's 2.54 times 12? 30 point what?
30.48.
Okay. And divide that out. Okay, 13.58. Now if you round to the nearest whole foot, what would it be? 14 feet. So back to our table. We have 14 feet. Okay. We have 10 minutes before problem of the day, so let's do another one. Let's do Venus. Okay, so we start out with our beginning ratio, 10 centimeters over 1.4 times 10 to the 6th kilometers equals something over, and for Venus we have 1.082 times 10 to the 8th power. So cross products, just like last time, we have 1.4 times 10 to the 6th times x is equal to what?
1.082 times 10 to the
Ninth power. Good. 1.082 times 10 to the 9th power. Next step, divide by 1.4 times 10 to the 6th. So work that out and see what you get.
How many places are we going to?
I think 3. What did you get this time?
0.773.
Times 10 to the 3rd power. So what would that be in standard form? 773. So back to the table. Now we have 733. And now we have to convert the centimeters to feet. Oh, sorry?
How'd you get 733, you said?
Oh, I wrote it in wrong. Sorry. I'll go back and fix that.
How come you wouldn't multiply by the 10 cube? Well, that's
Just a sec. Let me fix this. 773. Okay. And back here. Okay, Cody, what's your question?
how come you wouldn't multiply it? Oh, you did. Never mind. You're good. I didn't see I forgot about the decimal.
Okay. Other questions? Okay, so we have the 773 centimeters over 1. We'll be using the same conversions that we did in the previous one. 1 inch over 2.54 centimeters. And 1 foot over 12 inches. We cross off the centimeters and the inches. So we have 773 over 30.48, which is 25.36. So 25 feet when you round to the nearest foot. That was weird. It said it was sending project. I don't know where it was sending it to. But anyway, there it is. Okay, so the rest of those you would follow the same steps. Number 5, explain why all models that are built of the solar system are not built to scale. Why do you think it would not be built to scale?
Because it's difficult to make something so big so small.
Okay, yep. The solar system is just huge. In this case, they're starting with a ball that has a 10 centimeter diameter, so it'll be something like this, and that's the sun. And then you're looking at all these distances. Well, even the closest one is 14 feet away from the sun. Now, we didn't actually work out Neptune, but the distance in feet, you should end up with 1,056 in that very bottom right box. So we'd have our sun here, and 1,056 feet away is where Neptune would be. So it's unrealistic to really build it to scale. It would have to be out in some field somewhere. Okay, we're gonna skip number 6. The lesson wrap-up. What's the point? Exponent properties can be used to simplify calculations involving scientific notation. What did you learn? How to use exponent rules to simplify expressions that involve scientific notation and negative exponents, and how to use dimensional analysis with scientific notation to analyze problems. How big is big? Is it possible to build a model of the solar system to scale? Well, we already answered that on the previous page. Well, it is possible, Cody, but it would have to be outside in a big field. It wouldn't be possible to do it in a building.